Tonight we're going to talk about the word you use most often during the day, I think, time. Well, this being New York, and maybe the second most used word you'd use during the day. But time is universal. Think about all the times, and I'm saying it again, when you use the word time during the day. I don't have the time. What time is it? You know, do you have time for this? And it's a topic that crosses all disciplinary, issues. Like theologians wonder about time, and scientists talk about time, philosophers talk about time. And so tonight we're going to encompass all these questions that people have about time, like, when did time begin? When will time end? Is time real? Is it an illusion? Because these are things that scientists talk about, and they discuss these things amongst themselves, and we're going to bring that to light today, talking about time. And so everything you wanted to know about time is going to be discussed this evening. And we are honored to have a fantastic panel of scientists, philosophers who will come up here and talk about time. Let me introduce them to you. First, Paul Davies, a theoretical physicist and one of the world's leading expert on time. Paul, come on in and have a seat. He's professor at Arizona State University, and he's also the person that if we ever get a ET to phone in, you're assigned to talk to that extraterrestrial.
I'm your man, yes.
You're the man from Mars. He also has an asteroid named after him, Paul Davies asteroid. It's number 6870 in your program if you're looking to look up that asteroid.
It's not going to hit us.
What's that?
My one isn't going to hit us.
There you go. Also joining us is Max Tegmark. Max, he's a cosmologist who bridges theoretical and experimental physics. He's known as Mad Max. Is that right? Mad Max?
That's right.
Mad Max. He's a professor at MIT. He works with the SDSS collaboration. What does that stand for?
The Sloan Digital Sky Survey.
Wow, right out of Star Trek. Then that's on galaxy clustering, and he shared the first prize in Science Magazine's Breakthrough of the Year in 2003. Welcome, Max. Also joining us, we're our first of two philosophers. Talked about philosophers talking about time, because when you get into discussions about time, it's almost like talking about philosophy. Tim Maudlin, welcome, from NYU. He has authored many books that explore the mysteries of physics, quantum non-locality, and relativity. There will not be a test on this. Truth and Paradox, the metaphysics within physics, and the philosophy of physics, space, and time. And he's going to help us discuss it from a philosophical point of view, perhaps, this evening. Also, an aptly named guest, Craig Callender. He is professor of philosophy at the University of California, San Diego. He's author of the graphic text Introducing Time, as well as the editor of the new Oxford Handbook of Philosophy of Time.
It's a patronymic destiny. If your name is Crook, you become a crook. If your name is Calendar, philosopher of time.
There you go. Is the Oxford book a big handbook? A small handbook?
Yes, it's extremely large. It could break something if you drop it on it. It could break a table.
All right, we won't put it down here.
To talk about.
Let's begin with you, Paul. Let's talk about, you spend a lot of your time thinking about time. Let's set the stage. Let's turn back the clock a little bit. Set the scene for us and explain how Einstein decided to get involved with concepts of time.
Right, like all of us, Einstein lay awake at night as a teenager wrestling with the problem, what is time? And my favorite definition is time is just one damn thing after another. But he came to realize that there was a conflict, a deep conflict in physics, and we're talking about the turn of the 20th century. Deep conflict in physics between two things, one of which is very familiar. So you must have had the experience of sitting in a railway carriage and you think, oh, we're moving off, and it's the train on the parallel track going the other way. That's often called the principle of relativity, that uniform motion is relative. You're familiar with it as well. I don't know if you ever have this experience. A lot of people are afraid of flying. I do a lot of flying, so I'm not afraid. But the one thing that happens to me almost inevitably, as the plane taxis out to take off, I fall asleep. Just happens almost every time. So then when I wake up, I have no idea whether we're airborne or still on the runway. And that's because smooth flight, you can't tell. You can drink your coffee and play marbles or whatever, same laws of physics. So that's been known since the time of Galileo, that the laws of mechanics are relative. There's no, you can talk about my speed relative to you, but
right.
Nobody's got an absolute speed. So that was already known. But this was in conflict with what had been discovered in the 19th century about the way that light behaves. So light's an electromagnetic wave, and the equations for electromagnetism were all worked out in the 1850s by James Clerk Maxwell. And from the mathematics of those equations, well, I'm not going to go into that, but from the mathematics of those equations, it was clear that the speed of light is supposed to be a fixed number, a constant. Well, how can you reconcile the relativity of motion with the constant speed of light? Because what happens if you chase after a light beam? Can you overtake the light?
Right, that's what he was wondering.
Right.
Or if it's, what if I chase after this?
If it's coming at you, surely you'll encounter the light at a higher speed than if you're dashing away from it. And he realized these two pillars of physics couldn't both be correct. And the only way to reconcile them was to do something funny with time and space as well, as it happens. We're going to just talk about time. Basically, in daily life, we think that time and space are just sort of there. It's an arena in which the great drama of nature is acted out. But what Einstein said is no, that that space and time are part of the cast. They're part of nature, just like matter can be changed, manipulated, so space and time can be changed or manipulated. It's often called warping time or time dilation. So he had this idea that your time and my time might not be the same if we're moving differently. Well, I can demonstrate it right away. That we can introduce a time difference just by me walking up and down. That's all it takes. Now, you might say, but that must be a trivial amount. It's true, but if I took a plane, as I'm going to on Monday, to London, and then come back again and we compare your clock and my clock, if they're good clocks, we see there's a difference because we've been moving differently.
Wow.
And then
just the movement changes the clock.
Just the movement. But because light is the key to this, to get a really big time warp, you need to move it close to the speed of light. And in effect, what you are doing if you zoom off at close to the speed of light is you are leaping into the future quicker. So it's a sort of time travel into the future. It means you can get to a future event faster. So you fancy living to the year 3000 or here on Earth? Well, you can either do it the slow way and sit here for 1,000 years, or you zoom off close to the speed of light and get to the year 3000 in, say, 1 year. Right. So what it means is that the interval of time between two fixed events can depend on the way you move. So time is not absolute, it's relative, as we say. He also realized that gravity does funny things to time. Time, we're going to get into this later, runs, and I don't think time runs at all, but I'll use the words for now. Time runs a little bit faster up on the roof than it does in the basement. Once again, this is a measurable effect. We're going to talk later on how you measure these effects. So in other words, time is something that depends on how you're moving and what your situation is.
But we hear about the symmetry of time. What does that mean?
Right. Well, there's another big puzzle in physics, been around for a long time, which is that all of the laws of physics, with one minor exception, are symmetric under interchanging past and future. That is to say that the laws themselves don't have an inbuilt directionality.
The time could run in either forward or backwards.
To give you a very good example, so you take a movie film of the Earth going around the sun, like that, play it backwards, that's a perfectly acceptable solution of a physical situation.
But why don't we see it then? Why don't we see things going by us the other direction all the time, so to speak?
Well, the point I want to make is that simple systems reflect this underlying symmetry of time. But when we get to complicated systems, then there seems to be a directionality. And we see this all the time in everyday life. So this will be a scene familiar to everybody. Okay, so what we're seeing is an ordered state of matter spontaneously turning into a disordered state. Now, if we see this running backwards, you see everybody laughs because you know it's preposterous. But according to the laws of physics, that could happen. And so the question is, where does this asymmetry of time, this arrow of time that is so pervasive in daily life, where does it come from? How does it originate?
Do we know the answer?
We do. Well, I know the answer, but my colleagues may disagree. But Really, ultimately, you trace it back to the origin of the universe.
Right.
That the universe began in an ordered state, and it's becoming progressively more disordered. We'll get into that a bit later.
We'll get into that a little bit. Let me ask Craig, can you take us from here? What was Einstein's concept of time, and what did he think about?
Yeah, so I think it was really a fundamental reconceptualization of the way we think of time. So, from Newton onward, you think of time as having this, unique privileged present carving up the universe. If you think of a ham or something, and you think of it going through a deli slicer, there's one way of slicing that ham up. Einstein, on the other hand, thought, well, there really isn't any such thing as time and space. There's space-time, just these events which are inherently spatio-temporal. And I can carve that up in different, just like I could throw the ham in different ways and carve it up different ways, you could also carve up the events of the world into space and time in different ways, and that there's no unique way of doing that.
So so we had to unite space and time together to create a new construct?
Yeah, and I think, well, to me, I don't know what the others think, but you don't really see it so clearly in his original 1905 paper, but later in 1908, Minkowski, his teacher, really puts it in that framework. In fact, also there's a philosopher, McTaggart, who raised all these sort of puzzles for time in 1908 too. So 1908 was a bad year for time.
Max, what do you think?
Yeah, I think before Einstein, most people thought of space as this three-dimensional place where things happened over time. And then Einstein changed this viewpoint and said, really, we should think of reality as this four-dimensional space-time, where time is just the fourth dimension and nothing is ever happening. The past, the present, the future is in there. So if our life is a movie, then space-time is the entire DVD.
And you can travel within any of that time forward, backward? If you slice it up, can you get to all the slices?
Well, Einstein would say that the space-time is just static, like a beautiful crystal you can have in your filing cabinet or something. The DVD is not changing, right? It's wrong to say that the actor in the DVD, who's the hero, is traveling through the DVD. It's all there. And there are just these different moments in the actor's life that are in different places of the space-time, to now use Einstein's language. So it's a very different way of thinking about reality.
Yeah, Tim, I see you have a furrowed brow.
Yeah.
About all of this.
So let me just actually, because Max just said something that's often said, and I think it's misleading. He said, space-time is static, right? And we know what something that's static is. It's something that doesn't change with time. Now, time is in space-time. Sure, stuff changes. Stars collapse, right? Life evolves. All of this is physical fact. It's things changing with time, with a temporal structure. So, of course, even a long time ago, you could say there's a four-dimensional thing which includes the entire history of the universe from beginning to end. But to say it's static or things really aren't happening or so on, I don't think that anything really justifies. I wouldn't know what sense to make out of such a story about the world we live in, right?
Do you think it's just too much, maybe it's too philosophical, not based enough in real science?
No, I think it's as we'll see, I think it's a misinterpretation of what the mathematics is telling us, and a little bit of sloppiness about our language.
Yeah, so this is awesome. Philosophers always irritate us physicists by catching us when we use language sloppily. So let me retract the word static and see if I can say the same thing without using that word. We physicists love studying things mathematically. We study this mathematical structure called Minkowski space, which is a nerdy way of saying space-time. And we would say that space-time does not exist in time or in space for that matter, but rather space and time exist within it.
Within it, sure.
I didn't say static.
No, absolutely. And that you have to blend space and time together. I mean, as we'll see, you can actually sort of get rid of space at the end. A funny thing you can do in relativity is you can actually, instead of getting rid of time, what you can do is get rid of space. And we may talk about that a little bit.
We'll talk about it. Did relativity and Einstein talk about whether time changes? I mean, is it the same all over the universe, or is it same everywhere?
Intervals of time can be different depending on where you are and how you're moving, as I was explaining. So when I say intervals of time, between two fixed events, And the classic example that everybody likes to talk about is called the twins effect. It's sometimes called the twins paradox. It's not paradoxical. So supposing Ara, you and I were twins, so obviously born on the same day, same age. I go off in a rocket ship very close to the speed of light, and I go for, say, 2 years. And when I get back, I find you're 20 years older. I've moved so close to the speed of light, this time dilation has done that. So I've, in effect, leapt 18 years into your future. And people want to say, well, who is right? Well, we're both right. My time and your time are not the same. You stayed at home, I went in the rocket ship. We're both correct. The two end events, my departure and my return, we agree on. They're fixed events, but the interval of time between them depends on how you're moving. And we can measure this stuff, no problem. It's measured every day. We're going to hear a bit more about it, but most obviously with the global positioning system.
I want to move into that, but Tim is just chomping at the bit here.
Let me try again. Something I think is often said and is misleading. Go to your first point about relativity. You say if you go off near the speed of light, how fast are we moving right now? We're moving 99.99% the speed of light in some perfectly good frame. We're not moving any particular speed. Right. Now, what about the twins? Well, if you have two people in two cars and they start in the same place and they drive a while and their odometers start at 0 and they get back together and their odometers have different mileages on them, it's not really a paradox. They went different paths and their paths were different lengths. And what their odometers was measuring those lengths perfectly accurately. Every odometer went a mile per mile along their path. Well, that's all clocks do, and in the twins' case, the two twins follow different paths, and the paths are different lengths, and those lengths are the times along that path. And that's all there is to it.
Okay, well, let's talk about that, because in science, measurement is everything, right? You come up with a theory. Einstein has a theory. People have theories, but theories are no good unless you can perform an experiment and actually predict something is going to happen and measure whether that's going to happen. Let's talk about predicting Einstein was right. How do you prove, Craig, how do you prove time dilation? And time dilation is the idea that if you go close to the speed of light or you're speeding up toward the speed of light, time slows down, right? Would that be oversimplifying? Time for you.
Yes, but
how do you prove?
So there were a number of experiments, these classic experiments, where I think it was on the Concorde, right? The halfling and Keating. Oh, no, it wasn't the Concorde.
It was before that. It was back in the 50s, so they didn't have Concorde then.
Didn't they put a clock on a satellite?
Yeah, well, they did that too. But you're thinking of the Hafey-Keating experiment, flying around the world in opposite directions. Yeah. Pre-Concorde, I'm afraid.
So if you
Concorde would work better.
If you believe that if you get faster, if you move faster and faster close to the speed of light and time slows down a bit, you can perform an experiment where you have a clock that's standing still and a clock that's moving really fast and see if they keep the same time, and that has been done.
That's right. That was what was done. Was synchronize the ones on the planes to the one on the Earth, send the planes off in different directions, come back, and then they're not synchronized anymore.
The clocks don't measure the same time anymore.
No.
That's just from moving, from going to a faster velocity.
And the global positioning system's doing this all the time. So this is an everyday experience. If you took the time dilation out of the algorithm, taxi drivers would be lost within hours.
Actually, we should see how many experimentalists we have. Raise your hand if you have a cell phone on you with GPS. You found your way here, so your GPS is working.
Right. So this proves relativity.
Right.
Yeah.
So they use atomic clocks to prove these things. You need a really accurate clock, right?
We can do better than the traditional atomic clock, but this is the way that it was done back in the 50s and 60s, using an atomic clock. What is an atomic clock? Well, atoms are very good clocks. They emit light, or radio waves, electromagnetic waves anyway, at very precise frequencies. And if you've got a frequency, it's like a beat, like a metronome, and so the emission of light or radio waves by an atom gives you a time standard, and you can create a clock that locks onto that frequency, and that can be very, very accurate. These days we can go beyond that technology, and we were talking earlier, is it like to 13 significant figures?
17 now.
17 significant figures!
It's crazy, 17 decimal places.
You can measure time so accurately that now we even define the speed of light in terms of the second.
So this clock is so accurate, and it can measure just if you lift it off the ground?
A foot, the most accurate one, because when the gravitational field changes the geometry of space-time. And so if I lift something just a foot off the ground, A clock up here is traveling through a different patch of space-time than a clock down here, and has a slightly different geometry because of gravity, and you can actually measure the difference.
Wow! From the
from
changing
that
gravity,
little,
because
the
gravity
difference in the
affects time.
gravitational field at that level with the accuracy of the clocks.
Gravity slows
So
time.
when you're standing or upright, the clock in your head is ticking differently than the one over here.
And this also solves the mystery of whether you, Ira, are older or you, Paul, are older in the twin paradox, because he went off,
right.
you went off, so you accelerated, and he didn't.
That's
and
how you
Einstein
break the
said
symmetry.
that acceleration and gravity are kind of
Well,
two
wait a
sides
minute,
of the
but
same
didn't
coin.
he look at me and think I was accelerating?
No, you must.
I mean,
no,
I mean, if I'm accelerating away and you're on the Earth and I look at you, it looks like you're accelerating.
The uniform, the period of uniform motion. Of course,
Yeah.
you're right. There's a symmetry.
Let me
Good, good.
I got it.
But the
No,
symmetry-
this is wrong. This is wrong. Stop. Halt.
Jump in.
Clocks,
I don't want you to have
measure lengths. So you imagine your clock is going through space-time. It's following a path through space-time. What a clock measures is how long it is. And acceleration is how bent the path is. So if you're going through space-time and you suddenly change direction, you accelerate.
Right.
Clocks measure lengths, not being bent. The acceleration has nothing to do with the effect. The only thing that has to, and you know this is true, you can do it with gravitational lensing. The effect just has to do with different path lengths through space-time.
I don't disagree with that.
Key
That's
point we
correct.
want to
That's
get
correct.
clear up here, though, is that Ira is right. You cannot tell the difference between sitting still and moving uniformly. You know, Earth is whizzing around the sun right now at 30 kilometers per second. Can you feel it? No. But if you're in a car and you step on the accelerator real hard, you feel pushed back. You can feel if you're accelerated. What Einstein pointed out is you can't tell whether you're actually accelerated or just in really strong gravity. Right. But either way, you can tell you were being squished against the back of your rocket seat.
Sure.
Ira wasn't.
Yeah.
That's
so that
why
breaks the
That's
symmetry.
how that breaks the symmetry.
Because a lot of people
Yes.
think, oh, there's a paradox, because in
Yeah.
your reference frame, I should be aging
Right.
more. I think you should be aging more, but there's no paradox.
I'm not accelerating. No, you don't buy that.
But they agree. You could do this with two unaccelerated clocks. Gravitational lensing, right? You both agree. Send two clocks different ways around a star, gravitationally.
Yes.
Nobody accelerates.
Yes.
And they tick off different lengths, different amounts
Well,
of
it
time.
depends on their exact
But
trajectory.
it could happen,
If
right?
it was,
It
oh,
could
you
happen.
could do it that way.
So
yeah.
it's not the acceleration.
Well, let
no,
me
no,
move. Let me
no,
move.
no.
We can go on here all night, and
No, he's right. I
we'll
mean,
have a
we
beer
don't
later
disagree.
and talk
It's,
about it. But let's talk about how, because we're trying to talk about how do you measure this? How can you measure the effects and show that, test out Einstein's theories? We're talking about here on Earth with clocks and with special clocks. What about looking out into the cosmos? Can we look out there and see if there are experiments happening on their own that could measure these? Max?
Yeah, so we heard from Paul and you guys here that both speed and gravity can mess with the rate at which time flows. And what I love about being an astrophysicist is that when you look out into space, these aren't just tiny effects that you have to measure 17 decimal places to notice. They're huge effects. They're really in your face. To me, as an astrophysicist, the idea that gravity slows down time is just as obvious as it is to you that stepping on the brakes slows down your car. It's a big effect. And the most spectacular thing we can do nearby is just go to the monster black hole. It lives in the middle of our Milky Way galaxy.
That's not a real black hole, is it?
This is a really awesome simulation of it that my friend Andrew Hamilton made. But the black hole, I have bad news, is real. It weighs 4 million times as much as the sun does. This intimidating-looking circular disk that you see is the event horizon, the region where the gravity is so strong that nothing, not even light, can escape from it. That's why it's black, right? And the weird patterns you see around it are simply this powerful gravity bending the light rays, like we heard here. Just like a funny mirror in the amusement park would bend the light rays and make your face look funny. And we can actually go there without using hardly any rocket fuel at all if we go in an orbit that gradually spirals into it and parks in what I like to call the tourist orbit, which is exactly twice the radius of the Schwarzschild radius. It's an unstable orbit, so don't fall asleep at the steering wheel, because if you make a mistake, it might be your last.
Yes.
But while we're orbiting around there, our friends on Earth will see us orbit around a long distance there, about the same distances from the sun to the Earth, in 16 minutes. And how long does it take the sunlight to get from the sun to Earth? It takes
9 minutes.
Yeah, about 8 minutes. So that means people on Earth see us going at half the speed of light without using much fuel. That's cool. Fuel efficient time travel. And it's green. And yet, when we are in there, we will measure that it takes 16 minutes to go around. So our time has slowed down to half the rate, which means if I'm Skyping back home to Earth, to my mommy, I'll be going like, "Hi, mommy." And she will see not just that my brain is running slowly down there, but she will also see that the clock on board our spaceship and everything else is also running at half the speed. So she will actually correctly infer that I will not be able to tell from looking at Paul Davis and my other fellow travelers in the spaceship that anything is weird. It'll seem totally normal to us because we're all slowed down together. And instead, when I look at mommy on Earth, I will see her speaking twice as fast. So she'll be going like, "Oh, Max, I'm so worried about you. I'm so nervous that you're speaking so slowly, and I'm worried about you going to suck into the black hole." And I'll be like, "I'm fine, mommy."
You
and
do this very well.
This is the key principle of relativity that we just heard about, which is that you always think you are right about the flow of time and that everybody else is wrong. It's just like if you feel that you're having an argument with someone and you know you're right and they're wrong, and then it suddenly hits you that that's exactly how they feel too.
Right, right. Like, are supernova explosions a good source of looking for experiments with time?
That's another really, really cool in-your-face example. We've told you a tall tale here about all this cool stuff. Sounds good, right? But why should you believe a word of this? What's the evidence? Well, we've actually seen clocks run slowed down by black holes, because we heard from Paul that we can think of even atoms as clocks, where instead of the pendulum on Grandpa's clock, it's the frequency with which things are vibrating, that's the clock. And this is a really cool simulation that my colleague Ben Bromley made of how the iron atoms slow down near a black hole. And when they slow down, they emit light at a slower frequency, which looks red, as you can see here. And the best measurements we have of spectra of these so-called iron K-alpha lines confirm this and show direct evidence that the atoms near black holes have their time going at only half the speed. It's crazy.
It's crazy.
Very in your face. And if you have the next slide there with the supernova that Ira asked about, black holes are gravity on steroids, right? Now we have speed on steroids, because here we have a galaxy moving away from us near the speed of light, and we see a supernova go off, boom! You can see a flash going off there. For a brief moment, the supernova outshines all the other stars in the galaxy. We see it rise and we see it fade in a very interesting regular way, which was recently used to win the Nobel Prize in physics. And the cool thing is that when you look at supernovae that are really far away, traveling away near the speed of light, you see them blowing up, not poof, but they blow up in slow motion. You can really see the time has slowed down.
Time is slowed down.
It's not like David Wineland's atomic clock, where you need to measure 17 decimal places to see the effect. It's in the first decimal place. You know, it's a factor of 2.
Tim, you buying all of this?
There's a geometry, everything. The talk about their clocks slow down, I think can be misleading, just in my analogy about the odometers. Nobody's odometer was broken, right? If the two cars went different paths and they showed different lengths. All the clocks are doing what they should do, right? Which is measuring the local geometry of space-time where they are.
That's what I was going to say. So then, by looking at time being different in the black hole and to where time is here, so time is a local event. How time passes is a local event. It changes in different places.
Yes, the time structure is local in space-time. It's really things that are going on. You can think of the total time structure as a matter of what's going on in each little region locally, added up as you pass from region to region. Sure.
Huh. So does that mean we can, by going faster, you're saying we can actually go ahead in time?
Relative to somebody else, yeah. It's always relative.
So that's what science fiction movies talk about, maybe going.
Yeah, time traveling to the future is a done deal. We've done that. That's right. You get to the future quicker.
You get to the future
Going to the past is a whole different subject we're not going to get into. We decided we would quarantine that. We won't get into that.
Use the analogy to space again. If I'm flying in an airplane, why do airplanes fly over the North Pole? Because it's shorter. If I went just staying at the same latitude,
Right.
it would be longer, right? Paths between the same 2 points, some are shorter, some are longer. If they're shorter, and this is in space-time, it means your clock will tick off less time, you'll age less, you know. Right. So if you're only going to live 40 years, you can get to a different spot than you could if you went a very different way.
All right, let's move on about time because there's so much time to talk about it. Let's talk about when time began and will time end. I mean, are these more than philosophical questions? Oh, yeah. Okay, so Paul, give us an idea when was it the Big Bang the time began?
Well, coming back to Einstein, so once he'd established the idea, which now everybody accepts, that space-time are physical things. They're not just there, not just an arena, but they're part of the physics. They can change. One of the things that was soon discovered is that time can become so distorted, and space as well, that it in effect becomes infinitely distorted, and then at that point you would say time stops.
Because when it's infinitely distorted.
Right. Because supposing, you know, we've been talking about how clocks can get out of kilter with each other, if you like, run at different speeds. If that became an infinite effect, you'd think, well, what is going to happen? And the Big Bang, as is popularly called, the origin of the universe, could be one such point in our past where there is what we call a singularity in space-time, infinite curvature, infinite distortion. And under those circumstances, the Big Bang would be the origin of time. Now, when I was a student, everybody accepted that. They thought there was a Big Bang. Time began with the Big Bang. And at dinner parties, people always want to ask, well, what happened before the Big Bang and what caused the Big Bang? And you scientists think you're so clever, but you can't explain that, can you? Ha! You see. And I think Stephen Hawking expressed it very well. He said that asking what lies before the Big Bang is like asking what lies north of the North Pole. You can ask the question. It sounds like a sensible question. The answer is nothing lies north of the North Pole, not because there's some mysterious land of nothingness there, because there ain't no such place as north of the North Pole. In relativity, there ain't no such time as before the Big Bang in a simple picture, the picture that everyone believed in when I was a student. These days, we can't be sure that what we call the Big Bang was the ultimate origin of time. It could have just been a little local bang in a bigger system, which Max is going to talk about tomorrow, aren't you? The multiverse, which itself might be eternal, but each universe, each bang within that bigger system would have a beginning, but it wouldn't be the ultimate beginning of time.
So a lot of universes with a lot of big bangs
going on. Right, but no ultimate beginning of time.
No ultimate beginning.
So at this stage you could have either. You know, if you believe the simple picture, the Big Bang was the ultimate origin of time. There was no before. Nothing caused it because it was the origin of space-time and matter. And same thing with the end of time. Time can end. If we're looking at black holes, if you fall into a black hole, there may be a singularity at the center of the black hole. We don't know that. If there is, that could be the end of time for you.
But could it also be the beginning of time? If it's
portal,
like the Big Bang, isn't it like a mini Big Bang?
That's another theory, you see. So either time ends or it doesn't end. You know, if it doesn't end, then something else
has to go
to somewhere else.
They just raise the questions, they don't answer them. I mean, isn't it like, we were talking about this being like philosophy, right? Philosophical?
Could I add a point about this
Please.
to make it even more confusing? If you think of the singularity that Paul talked about as, you know, that it's ill-defined because the curvature goes infinite, and you model this like the real number line, say between 0 and 1. And so you think of the real number as all the decimal expansions. And so now you take that point 0, think of that as the Big Bang. It's ill-defined, so pluck it. So remove that 0 point. Well, if you do that, you know, what is the next number? Well, is it 0.0000001? No. It's 0.0000, etc. No. There is no first moment. There is a first second, though.
There's no moment, but there's a second.
So there is no first moment of time.
But there's a first second.
So long as time is continuous.
Yes. Yeah, and another way of restating what Paul just said here about north of the North Pole, if we come back to this metaphor of thinking of the cosmic movie sitting on this cosmic DVD, which Ira conveniently has, then if we ask, what happened before the beginning of the movie on this DVD? Well, sorry, this is a DVD. That's what there is. At the same time, with all my work on actual data and experiment, I think, to be honest, and put it in very technical terms, I think we have no clue what really happened early on. We have a very good clue of what happened after that during the next 13.8 billion years that we'll talk about. But it's fascinating, as we just heard here, how it's gone from being that, well, in the beginning there was the singularity of general relativity, to being a field now with really active research and loads of different competing ideas that people actually argue about, not just in bars, but actually at physics conferences.
But I think that's also because at a certain time, people were learning general relativity. If you take those laws as sacrosanct and exact, then you can actually prove that there's a singularity. I mean, it's a mathematical theorem. But of course, everybody knew these aren't the final equations, right? There were going to have to be corrections to them.
To the laws of physics.
Well, certainly to general relativity.
Laws of physics.
General relativity only covered gravity and only covered it probably at a large scale. Now, they're well-defined equations, and you can study them with mathematical precision, but they're not the right final equations of physics. And of course, we only really know if there was anything before the Big Bang and what it was like if we get to a final theory and we can analyze it.
It's a lot of work for you guys.
That's their work.
On the case.
You know, talking about the Big Bang is what happened before the Big Bang. Reminds me of the question we get asked often on Science Friday, and other physicists from Einstein down said, well, if the universe is expanding, what's it expanding into, right?
It drives me mad when people ask that.
Yeah, well, we heard from...
Well, it's the reverse part of that question of what came before the Big Bang.
I just heard you with a guy on Science Friday who explained it very well.
Yes.
We heard already from Paul here that Einstein said space isn't just this boring, static 3D thing. It's something which can be stretched out. So we tend to think of space kind of like what we learn in the news about the Middle East. You can only get more space by taking it away from someone else. So you can only expand out if you say, move over, dude. Whereas actually, Einstein said that space can stretch out. So our universe is right now creating more cubic meters or gallons of volume, without it taking away from anyone.
Expanding.
Yeah, not this room. Woody Allen pointed it out. But between the galaxies, far apart, are new gallons being created all over the place, and they're not being taken away from anyone else.
Well, let's talk about the size of the universe, because I know that's what you measure. How big are we expanded to? What are we up to now?
So this is fascinating, because when I'm still not that old, right? When I started grad school, started my career in cosmology, we were arguing about whether our universe was 10 billion years old or 20 billion years old. Now we argue about whether it's 13.7 or 13.8 billion. So what happened? Very briefly, what happened was data, like the stuff you mentioned in the intro. And if we imagine data, numbers, hard measurements, because if we imagine for a moment that I'm looking at our universe, and each one of you in the audience is a galaxy, then the first thing that would strike me is that you guys are all blushing. You here in the front row are just blushing a little, but some of you guys in the back are like tomato red in the face. So what's going on? All the galaxies are actually looking redder than they should. Well, we know that if galaxies are emitting red light with lower frequencies than it should have, that means its atoms are vibrating too slowly. So time is slowed down in these galaxies. And we just learned that if the time is slowed down in these galaxies, it could be because they're moving really fast away from us. And in fact, that's exactly what we mean when we say our universe is expanding. Okay? So as a cosmologist, I love the weird stuff that happens to the flow of time, not just because it's cool, but because it's really useful and helps us measure these sort of things. And we've measured very accurately now. That's one of the things we did with the Sloan Digital Sky Survey. We tried to make the biggest 3D map of our universe so far. We measured very accurately how fast different galaxies were going away, and we found the more distant ones go away faster. And this is exactly the same principle as a cop would use if he stops a car for speeding, saying, hey, my radar that bounced back from your car was going at too low a frequency, so you must have been driving 100 miles an hour, or you're busted. Right? And if this cop now notices that in your car, right, that you have all these diamonds, which you've obviously robbed from a jewelry store, he could figure out roughly when the crime happened by just taking the distance to the jewelry store and dividing by your speed, right? And we can do exactly the same game with these galaxies. We take the distance to a galaxy, divide by the speed, and ask how long ago was it here? And when we correct for acceleration, we get about 13.8 billion years now. So we have the time of the crime. And moreover, by using these weird time effects, again, just to measure stuff, they come back to Ira's question of how we really know it's 13.8. The next thing I would notice, if I look at it, you in the audience again, is it's not just that you're blushing, but there's another weird thing going on. I see that you look younger and younger the farther away I look. I see a lot of canes and walkers in the front.
There, so
yeah, there's a lot of spitballs in the middle of the room, and I see a bunch of kindergartners there, and toddlers, and some babies. And then it looks like just the same way as you can see in the universe slide I made up here, where the nearby galaxies are old and mature and big, faraway galaxies, small baby galaxies. Why? Because it takes time for the light to reach us, so looking far away is like looking into our past. And if you look real close over there, it looks like the organizers kind of blew it with the ticket sales, because the last 10 rows are empty, there's no one in there. Just kidding, but that's what the universe looks like, right? We see there are no galaxies beyond a certain distance. When we look so far away, they hadn't had time to form. All you have is this transparent hydrogen gas out of which the galaxies were formed later. And if we have the next slide, that means that when you look still farther away, you see something else really funky. So if I look out into the room, I notice the back wall there is glowing with a strange incandescent radiation. That's exactly what we see in our universe. Because when space expands, the gas cools off. That's how your air conditioners hopefully work today, right? And so in our early universe, this gas is hotter and hotter and hotter. And sufficiently far back, it's so hot that it's a hydrogen plasma, which is opaque. So it's just like the wall. You cannot see through it. It looks to us as if beyond all these galaxies is a wall of glowing hydrogen plasma. And next slide, please. We, of course, see that in whatever direction we look. So the way it appears to us humans is as though we're actually surrounded by a giant plasma screen. This is the so-called microwave background radiation. And this was on the front page of the New York Times just the other month, the Planck satellite image. I can put it in here. The way
that's not the Earth, that's the universe.
That's our universe. We're in the middle of this, and what you're looking at, this ball, is the spherical region from which light has had time to get here so far.
What's on the outside of that thing? No.
If we wait this another billion years, light from there can reach us, and we can find out a bit more. But
why does it have different colors in it? What do the different colors mean?
It's cool. Good question, because these baby pictures of our universe are showing us what this plasma looked like when our universe was just 400,000 years old. And if it looked exactly the same color everywhere, if space were completely uniform and boring, it would have to stay that way. And you would never make any planets or stars, and this meeting would be canceled. Fortunately for us, there was a little bit higher density in some places than others, so you see some hot spots and some cold spots in that map. And over the years, and billions of years, gravity amplified these tiny clumps to big clumps like galaxies, stars, people, and the World Science Festival. So to summarize, I think what we've really learned is that this business of time acting funny isn't just a cool thing. It's extremely useful, because every single fact I told you ultimately is something we've learned as scientists from using that effect, to our advantage.
How far back? You said you got back to, how far back was that? To 400,000?
So we can see, 13.8 billion years ago, 400,000 years after the thing that we have no clue about.
How far back do you theoretically think? Can you push it even further out to see?
Yes.
Far how?
Theoretically,
we can.
as far as you like.
How far?
I mean, the main problem is we can't see through that plasma screen.
Right.
But if you go to the doctor and he says, sorry, I can't see if your rib is broken because you're not transparent, Ira, you're going to be like, come on, give me an X-ray already. Right? And sure enough, there are other kinds of radiation that can penetrate that. For example, neutrinos, and even gravitational waves, ripples in the very fabric of space-time. And the next sensational big thing in cosmology will be if we detect these gravitational waves from 10 to the power minus 34 seconds after our Big Bang. This will happen if the inflation theory is the correct answer for what happened early on.
Right.
And if it happened in the simplest possible way. And if it happens, it'll definitely be all over the Science Friday, in a year or two.
White on rice.
Right now, the frontier of our ignorance, I'd say, goes at about 1 second. We can't see it, but there's sort of fossils left over from there. Just like we know the dinosaurs were here, even though we can't see them. We see we know that if it was super hot, 1 second after our Big Bang, the hydrogen there should have done exactly the same stuff as super hot hydrogen does in the middle of the sun, fusion.
Wow.
And we see the products of it, and it all matches.
It's worth pointing out that the Large Hadron Collider
Right.
recreates conditions that would have prevailed about a trillionth of a second after the beginning. So we can sort of make little patches of Big Bang in the lab.
Okay, let's move on to a question that I've been dying to talk about time, and I've been reading and talking with people about, and that is time an illusion? Is it, we talk about time, you experience it, but to some scientists there's a great rift between the folks who believe time is real and time is an illusion. How can time, Paul, tell us about time. How is it time real, or why do some people say it's an illusion? Well, let's get into this.
Right. You've got to be really careful to distinguish when we talk about an interval of time or the passage of time. So I don't know.
Already you lost me here.
No. I don't know many people who would say that we're doubting the fact that this session here is going to last 1.5 hours, and we can measure that, and that is a meaningful statement. So that is one thing. But when people talk about time being an illusion, what they really mean is the passage or the flow of time. Now, we've been very sloppy with our terminology. Even Max was talking about the flow of time being faster. You were talking about time passes, and I said, don't say that. Don't use that word, the P word.
P. I didn't know that.
Hermann Weyl expressed it very well. Time does not pass, it merely is. And so we're back to this whole issue about the DVD, about block time, as is the technical term. We have space-time, it's just there. I like to call it the timescape. We have the landscape. You can unfurl a map that represents the landscape. In the same way, we've got the timescape. Everything is there. You have all events for all of space-time simply there. I don't think anybody claims that's an illusion. So measuring an interval with clocks between two events is real.
Okay.
But the question is, what about this impression that we all have in daily life that time is flowing or moving? And
you have a video that illustrates.
And we do, and I think it's an illusion, but I'd like to be persuaded otherwise. And this is my favorite analogy. And so now everyone has had the same experience. You spin around like that and stop. You have this overwhelming impression that the universe is rotating. Okay, you feel it's this dizziness. Everything's going around when you stop. But you can look at a spot on the wall and you can see, of course, it's not rotating. Your observations show it can't be rotating. It feels in your head like it is rotating. In the same way, I'll demonstrate this.
We'll sing.
Where was I? Yeah. So in the same way, you can't get away from this idea. It seems to be whizzing along.
Yeah.
But when you stop to think about it, well, doesn't really mean anything to say time is moving, because movement is the change of something, position of a point with time. But what does it mean to say that time is changing with time? It means nothing at all. You say time changes at 1 second per second, but that's just a tautology. What else could it be? 2 seconds per second? And so to a physicist, and in fact this was the famous quote of Einstein, to a committed physicist, past, present and future are only illusions, however persistent, and this whole idea of a universal now and a march of time, I think Craig's going to show us a video shortly about this. It doesn't mean anything at all. So there's a huge conflict between our daily experience that time is passing and the physicist's view of time that has no place within any of those equations. There's no device that can measure the flow of time. There's a device that measures time intervals. It's called a clock. No device that can measure the flow of time. No timeometer, so to speak.
Right.
And so there's a conflict.
No, I agree with Paul, and what I've been working on a lot lately is, so this illusion of time flowing, I think it's really important to us. It's the way, it's really the time of our lives, if we look at the first animation I have. So I think we normally think, as we navigate through life, we normally think that there's, time and space, And we think that there's this, this moment right here that I'm talking to you right now, you coming to this event is what's happening. This is the present. It's moving through, sweeping through world history. That there's this, but it's leaving behind this fixed and settled past. And in front of you, so my birth is there, Socrates' death. In front, though, there's this open, ripe with possibility future. So right now you could change your actions in some way and become a philosopher or a plumber or whatever. It's not there yet, you think. And as you navigate through life, you think that you have this. It's all fixed, this past. Whereas the future is all open. And it makes a real difference to you. Your attitudes about the past and the future will differ in all sorts of different ways. And so it's really important to us. I think it's wrong. So physics tells us, I think, that it's wrong. So relativity tells you that present, there is no unique one. And so you could carve it all up different ways. And so then that means, hence, what's fixed and what's open, there's no fact of the matter about that either. Is what events are really open to us and that is just not fixed. And so notice three things about this picture. One, you've got the present being really special. That's what's happening right now. Two, it divides up the past and future, and you attribute different properties to this past and future. So you think one is fixed, one is open. And then three, it updates. So this whole tripartite structure is updating itself with each moment. It's all complete rubbish. But why? Why? So if you go anywhere, any culture, all people believe this. You could even do, in some sense, tests on animals, and they in some sense, have to operate with a kind of model like this. Well, why? And so I've been trying to figure out, how, give a story about why creatures like us, come up with this kind of conception of time, even though it's wrong. And so, first, I think it's really an interdisciplinary thing because it really requires some philosophy, physics, psychology, a whole bunch of different features that go into explaining why it is we come up with this. And so the first thing I want to explain is why we feel like we're trapped in this present moment, why we're stuck in time, if you like. For that, you need some physics and you need some psychology. So the physics first, if we run the next animation. So here I'm going to talk about, imagine slicing the world up. It's a little weird to think about, but imagine slicing the world up the normal way where you have all these spatial moments, one after the other, versus slicing it up, grabbing this 4D block that Max talked about, his DVD, portions of the DVD. Imagine, so this is the normal slicing.
So those are little slices that are good.
That's right. So those are different moments of time going up in time. But you could also imagine grabbing, some other plane of space and time and moving out, say, to the east direction, or slicing, in terms of the different avenues in New York over time and moving across New York, across Manhattan that way. But if you did that, you would have a very unwieldy physics. You won't get as much information. It's really important that we that we carve up the world the way we do. If you look at in that animation, that ball, in the second animation, it becomes two balls, or if you like, it has or one ball going back in time. But that's not the way we think about things, and so we've got this time being one-dimensional. There's no backwards time travel, and so that's the physics part. The psychology part. Well, think about the fact that. So when you're listening to me right now, hopefully I don't seem like a poorly dubbed Godzilla movie. So my lips, the image, the visual impression of my lips hopefully matches the sounds you're hearing. Although, it's bouncing off the light is coming in, bouncing off my face at 300,000 meters per second. The sound is coming in, woefully slowly at 300 meters per second. And yet, your brain is putting the two things together. And you're doing this all the time, And it's happening so quickly, so we can see how, there's certain thresholds at which we do it. And it's very interesting to see why we do it and when we do it. If we look at, so here we'll see a test here, so see how many people can tell which of these two dots happened first. Anyone? Could anyone tell? All right. Yeah, so that's like right at the envelope of it's 40 milliseconds, so it's right at the envelope of when people can tell the difference. The next one, people should be able to tell the difference. And now the next one, this one should be really easy.
Put up the same hand.
Yeah. And so we don't really notice this, but all the time our brains are doing this. So when it's thunder and lightning, it's the same event, sound and light, but our brains say, no, we don't bind those two things together. But other things we do think of as, see as subjectively simultaneous. And there are all sorts of interesting experiments too. So if you think about ventriloquism, when you have a puppet, and what the puppet is doing is in space attracting the sound, right? So the puppet, the ventriloquist is, by making the mouth move, is attracting the sound over to that bit of space. But you also have time versions of this. So you have temporal ventriloquism, where you can have flashes attract the sound, or you can, the other way. You can have the sounds attract the flashes. No, wait, the first one was right. Sorry, you have the so the other one just is regular ventriloquism. And so you have all these sorts of, you don't even notice what's going on, but your brain is doing all these sorts of tricks. It's getting bombarded with all the, think of, if you think of an explosion, you'd have, heat waves, so there's pressure waves, light, sound, all sorts of things coming in at different signal speeds, and yet you'll, put it all together, and more or less, for macroscopic salient events, you'll get it all match the objective order in sequence. All right, so that's the psychology. There's a lot more to say about that, but put the physics together with the psychology. Why do we think that the now, that present, is really special and objective? Well, it's because there's going to be a massive intersubjective agreement about that. So I can just, I reckon, say, if one of these, lights, or if the curtain was about to fall on me, he could say, "Look out." He doesn't need to say, "Look out now." Or he could say, "Look out now," but he doesn't even need to say, Craig, synchronized watches. It's whatever GMT, ready, look out. We can just, because the time he says it, that lag time between the time I process it and the time he also then processes it is so fast that there's going to be this intersubjective agreement about it, and we could just use this shorthand, now, or we could even drop the word now. On the other hand, if you think of in space, I don't think of the here as special. Why? Because we can walk around in 3 dimensions in space. We can do, because we can't time travel, but we can space travel. So if you think about it, we can sort of bend backwards in space. So I could just walk around back and forth in all these different spatial directions, but I can't do it in time. And so there's going to be this massive intersubjective agreement about the now, and we're not going to find a spatial counterpart of that. So if you bear with me, just quickly, I'll mention, is it okay? Two other things. Quickly? Okay.
We're running out of time.
Yeah. The other thing is, so why is the past theme fixed and the future open? Well, that's a puzzle. We have this causal asymmetry we know about. If I wiggle something, it'll have downstream effects into the future, but not the past. But that's true of all times. Why do we think that the past is fixed in this way? And I think it has to do with the fact that whether we have it really or not, we have our subjective impression is that we have this sense of free will. And so there are all these self-fulfilling predictions I can make about certain ranges of actions, and that leads me to think that I have that the future is always open, and I don't have that about the past. Think about the waiter is coming. You've decided what you're going to have for dinner, and you're thinking, I'm going to have the chicken, I'm going to have the chicken, I'm going to have the chicken. The waiter, and maybe everybody here says, he always gets the chicken. He's going to get the chicken. But I can always, ruin your prediction. Right at that last moment.
Go for the salmon.
Fish. Yes, I go for the fish, and then, and I made it so, and it seems to me that I made it so, and it's going to seem really open to me. Okay, so that's the fixed business. Why does it seem like I'm moving up through time in this way? So it seems like I'm getting closer to my death. But if this Einsteinian picture is right, it's already there. The past is already there. What's moving? There's nothing moving. Well, the way I think about it is you've got all these memories, and you've got these, and they're nested. So you've got memories, but not only memories, but memories of memories, and memories of memories of memories. And with these, this asymmetric stock of resources, you devise this story of a self. So I'm telling the world the story of myself, the story of Craig. And it's a fiction, but the fiction is moving up the line. And so this is what gives me this idea that I have this, so that I think of the ego as moving. And once you have the ego moving, then I think you've got time moving. There's a nice little experiment that's done where people say, get you to shift between these two perspectives, an ego moving and time moving perspective. So if I ask you, I say, next Wednesday's meeting has been moved forward 2 days. Now, which day is it on? Is it on Monday or is it on Friday? So people will switch back and forth. So some people will say Friday, some people will say Monday. It shows you can switch back and forth between the sort of ego moving and time moving perspective. And so then I think these are the three components for explaining this, why we have this illusion that Paul talked about.
Well, Tim, I know you're chomping at the bit here because you don't.
I'm the only sane person up on the stage, apparently.
You don't think time is an illusion at all?
No, I sometimes say I'm a wonderful professional where I can actually put food on the table, going out giving papers to defend the thesis that time passes.
Time passes.
Not for
these guys.
You
believe time is flowing.
I believe time passes. I believe it passes in a definite direction. I believe I can now decide what to have for dinner, and it can depend on what I do now. And I can't now decide what to have had for breakfast this morning, right? That is beyond my power.
That's nothing to do with the passage of time.
It does.
Time asymmetry.
In fact, it does, right? The future is differently oriented to the present than the past is, and that there is an intrinsic directionality to time. And we are all getting older, unfortunately, and closer to the grave at the end of this show than we were at the beginning. So I think these are trivialities. I think they're also true, and I think physics doesn't say anything that suggests they're not true.
There's no directionality to time. There's a directionality to the world in time.
No, I think there's a directionality to time. Time itself is a directed geometrical object.
How do you measure this directionality of
I can certainly measure
itself?
Easily enough, a million times in a laboratory, you do measurements about what happened first, then next, then next.
Yeah, that's just
earlier and later is an asymmetric relation. It's not the same as, earlier and later is an asymmetric relation.
It's not if you just have a periodic process. It's completely symmetric.
The world is not periodic.
No, and that's the arrow of time.
Processes.
That's got nothing to do with time. And it's got to do with the initial conditions of the universe.
Earlier and later is still asymmetric, even a periodic process. You just keep coming back again and again and again, over and over.
But you're talking about states of the world. You're not talking about time.
I think this passionate disagreement about the words actually hides a bit of an underlying agreement that you have. I think it's more the choice of the words, really, than the substance.
I don't think so.
I don't think so either.
I don't think so.
I'm just trying to...
you can try to smooth this over and make them look like they're agreeing.
I had him use the people.
I'm sitting here and I'm hearing him say something totally different.
I don't think the word illusion... Look, there's an interesting question how we perceive time. It's a complicated... The same way with space, right? You see the Mueller-Lyer arrow things, where the one arrow looks longer than the other. And you measure it, and they say they're really the same. So that's a kind of visual illusion. You don't say space is an illusion. Okay, so there is complicated neural processing about how we come up with our perception of time. I don't think that has much to do with physics. It's an interesting separate question, not to do with the physics of time, which is much more basic.
Well, let me move on. Now we know where you stand on this. You have come up. Let's move right to your radical idea. You've invented a new math.
Yes, I have.
A new math.
Absolutely.
See if you can explain it to this
audience.
All right,
here we go. This is going to be fast and serious and incomprehensible. So we've been talking about space-time, and we've been talking about time as part of the geometry of space-time. So what do we mean by geometry? What kind of structures do we have in geometry? Well, we just saw in Euclidean geometry you have straight lines and circles, that's distance things. But there's a more deeper underlying geometrical structure called topology. And the idea behind topology is that certain features of figures remain the same even when you stretch the space, as long as you don't tear it. So you saw when you stretched the space there, the straight line became curved and the circle was no longer a circle. So those are not topological features. But still the dot remained inside this closed figure. So that is a topological feature.
Right.
So if you think of time as part of the geometry of space-time, you have to ask, well, how do we understand geometry? We do it through math. We do it through a particular mathematical theory that we use. It's our lens by which we look at this. Now, what I think is that we've been using the wrong one. Okay? We've been using the wrong mathematical tool. So what we want is a feature that remains unchanged even when you stretch. Now, what normal topology does, you take a circle and you take its circumference off, so it has that fuzzy edge. And you notice as you stretch it, it still has a fuzzy edge. There's still no boundary to the circle. So the boundarylessness is a property that's invariant under this stretching. And standard topology uses that as the basic organizational structure. And that's called an open set. A set that doesn't have a boundary or it doesn't have an edge is an open set. And then standard topology lays down some axioms about the open sets. I'm just going to list them here. The whole space is an open set. The empty set is an open set. If you have a bunch of different open sets and you union them together, you join them all together, sort of merge them, that's an open set. And if you have two overlapping open sets, their intersection is an open set. That's the standard mathematics says that's what open sets are like. You specify the topology of a space by specifying the open sets, and then you analyze it. Now, I think that was the wrong place to start. Okay? I think it was the wrong structure to grab. So we need another structure that's invariant under this stretching. Well, here's one. Think of continuous lines. You remember, in Euclidean geometry, we used a pencil. It draws continuous lines. They remain continuous lines under stretching. So I'm going to take those things, lines, and I'm going to throw away the closed line. I'm going to throw away the circle. So just take the open lines, the ones that don't come back on themselves. I'm going to say that's the basics of the geometry. The most fundamental, deep geometrical structure is given by the continuous lines. What am I going to do with that? Well, I'm going to have some axioms that tell you what lines have to be like. Simple axioms. Every line has at least 2 points. That one's kind of really easy. This is really not very complicated. The next nice thing about lines is that they're made up of shorter lines. If you have a line like that, you can cut it into pieces like A, B, and C. All of those are lines, continuous lines. But A together with C, those disconnected pieces don't make a line. So that's an axiom about what lines are like that these things have to satisfy. And then there's another axiom about how you can make longer lines out of shorter ones. So if I have a line from A to B and another line from B to C, I can join them together. If they overlap the right way, I can join them together to make a longer line. So I've got, just as in the standard theory, there are 4 axioms here. I've got these 3 axioms about the ways lines behave at this very deep fundamental geometrical level. Now, the interesting thing about lines is that you can put directions on them. All right? So we talked about the direction of time. If you say, put a direction on an open set, I wouldn't know what to do. There's no mathematical operation that corresponds to putting a direction on an open set. But if you give me a line, I know what you mean, put a direction on it. Okay? So I can talk about directed lines. So the idea of directionality is going to be very deeply built into the mathematics here. So let's try and think about space-time in terms of this. How about Euclidean space? 3-dimensional Euclidean space. All kinds of nice continuous lines that run around in all different directions. Those would give me the very deepest, most fundamental structure of Euclidean space. And I've put arrows on both ends, because a line in space, if it goes from A to B, it also goes back from B to A. It doesn't have a directionality to it. But let's try and do this with space-time. Now, here's the old classical space-time, the one that Craig talked about with these slices, these simultaneity slices that run, that chop it up this way. And there's the sun and the Earth orbiting around the sun. And what I would like to do, what you can do, is describe this geometry in terms of these lines. It's kind of a complicated thing to do because you've got to describe these horizontal slices, and then you have to describe these other things. The beautiful thing is that if we give up classical physics, the one that we thought, that's what time, we always thought of time in classical physics. If we give up classical physics and we go to relativity, The fundamental structure in space-time doesn't look like this. It's much simpler. The fundamental structure of space-time in relativity is a light cone structure. That's why light is so special in relativity, because at every point in space-time, there's where light would go if you emitted it from that point, or how light could get there. And that forms a fundamental geometrical structure. That's the relativistic structure. Relativity is sort of most of it built into just this space-time. So now you have a nice suggestion. You can't do this in classical physics. You can do relativistic physics. Suppose I now have a relativistic space-time. There's the Earth orbiting the sun, always staying within the light cone, because the Earth can't go faster than light. So its trajectory, its line, always sits inside the light cone. Take as real, take as fundamental in the geometry of space-time only those lines, the lines that a particle could travel or the lines that a light ray could travel on, and get rid of all the rest of it. Throw the rest of it away. All that's left. Now, what's special about those lines? All of those events are ordered in time, have a definite time order. And because we can put arrows in at a basic level on this, we say, well, furthermore, time goes a certain way, okay? In the mathematics, if you switch the mathematics, I think the reason it's hard for physicists to see the direction of time is they used a piece of mathematics that was developed to analyze space, and there is no direction in space. So you have this mathematical theory built for something with no direction in it. You then try to analyze space-time, and you say, gosh, I don't see a direction anymore. It must be an illusion. It's not an illusion. We're getting older, right? It's not an illusion that actually I can make a decision now about what to eat for dinner and not what to have had for breakfast, right? Those aren't illusions. And the reason physicists sometimes think they're illusions is they're using a mathematics where they're not easy to see. You switch the mathematics, everything's going to work out very cleanly, and you'll stop hearing all the strange stuff about how it's just an illusion.
Because he's conflated the flow of time with the time asymmetry. And I've worked so hard through my career to separate these two. Of course there's an asymmetry of time. There's an asymmetry of the world, states of the world, in time. Nobody here would disagree with that. There are later states and earlier states. Older people, you get older, younger, all the rest of it. Of course that's true. That's a property of the world in time, property of states of the world in time. It's not a property of time itself. You can draw a diagram and put an arrow on it if you like, but unless you can actually physically measure such a thing, it's meaningless. And what we actually measure in the world are sequences of states like the falling glass and so on. That's time asymmetry. That's not the flow of time. That's not this psychological impression we have from the laying down of memories and all the other stuff up here. The time is moving. Time isn't moving. That's an illusion. Asymmetry of time is not an illusion. It's real, and it's a property of states of the world, and it originates in how the universe began, the initial state of the universe.
Can
Agree?
Agree? Also, sort of follow up to this, so he can answer them both at the same time. No pun intended. So I agree with Paul's sentiment here, and I want to add, since I'm all about measurements and experiments, you have this very intriguing mathematical theory. We also have this very successful mathematical theory of Einstein, general relativity, which has passed all these tests, explains the GPS stuff, all the weird stuff we observe near black holes and in our early universe. So there are two logical possibilities. Either your theory predicts exactly the same thing as Einstein's for all the measurements, or it predicts something different that we can test. So which of the two is it?
You're thinking the wrong level. What I did not produce was a physical theory. What I produced, mathematics is the language in which you write physical theories.
So
okay? It is the language in which you articulate a physical theory.
But there are no
now,
options.
You can re-articulate Einstein's equations in this language.
Is that possible to do that?
Sure.
So then you're
Yes.
saying you
And
don't...
do you come out, has somebody done it?
I can do it.
So
It's
he's asking, did you come out with the same results?
No, of course you're going to have, you're writing the same theory in two different languages. If I translate a novel from English into French, it better not have a different ending.
But you're saying...
Right? It better not have different predictions when I translate it from one language to another. It's just a mistake to think that what I'm doing is something that would give to a different prediction. I'm trying to state the physics in a language in which its implications are clear.
I think he answered yes to your question.
I think the answer is no. I think
it has no observable consequences.
I think you're saying, and correct me if I'm wrong, there are only two logical options, yes or no, right? Either you predict that all experimental tests will agree with general relativity?
Yes.
Or they
If
won't.
you rewrite general relativity in these terms, you'll get all the predictions
But
of
then I
general
would
relativity,
say
of course.
it's an equivalent mathematical theory. You're just putting different words to the exact same mathematical equations.
That's
It's just a bunch
actually
of blah, blah, blah.
it's really a different mathematical tool. It actually has makes different judgments about things. Not experimentally, but there's not enough time to talk about it.
Fact of the matter. I mean, so once you've constructed the space-time, do you think there was a fact of the matter about how you got there?
What do you mean, how I got there?
How you constructed the space-time?
I'm just.
He's asking,
I would
does it matter
answer-
how you got to the answer? Is that what you're asking?
Yeah. So if you end up with a
come up with the same thing as
space-time
a-
model, and now you've given a story about how you get that space-time model.
I'm going to end up with something where there is an intrinsic direction.
But he's
to space-time.
disagreeing with your whole
we keep
premise.
having this
And
question
does it
about
matter
what's
which way the arrows are pointing? Couldn't I do the same thing
I mean,
the other
if
way?
the arrow means there's an obvious, completely conventional issue about what an arrow means. Right? When I put it one way and I put an arrow this way, it's a convention that the arrow points in the direction you can go rather than the direction you can't go, right? We could adopt the other one.
But
the point is, what the arrow represents is this
from-
fundamental
Big confusion
asymmetry in the
to-
direction.
Big
I could get this
I knew
model
I'd get
from
the herding
later
cats
than
tonight.
relation
Big
rather than the earlier
confusion
than.
about the arrow. So two new
Let me
conventions.
go this way. We'll walk
so
down.
Two
Paul, you-
conventions about
Okay.
arrows, and they're often conflated in exactly this muddle. One is when you use an arrow like on a compass. Compass needle,
Right.
it's pointing north. It doesn't mean you're moving north. The other is the arrow that you release from the bow. It's moving. Okay, so arrows are a metaphor for two completely distinct things. One is an asymmetry. The compass is the asymmetry in the North Pole and South Pole, and the other is motion. And nobody denies the arrow of the asymmetry, the arrow of time I've been talking about, the asymmetry of the world in time. That's one arrow. The arrow of motion or movement, the flow of time, the passage of time, all that stuff, that's the thing that is the illusion. That's the standard physics position.
Well, he's saying
trying
you're
to
using
defend.
the wrong tools to measure
He doesn't.
them,
Yeah,
right?
Tim-
You're using
Tim-
the wrong tools to make the point.
So,
He's-
so if Tim's reformulation of this has no observable consequences, I'd rather stick with what I know and understand, because I think it's just conflating a lot of issues, like the two metaphors of the arrow get conflated. It just does a disservice to the subject.
And I love that it's heating up here.
Good,
It's getting really fun. Thank you for raising the temperature, Tim. That said, I think it's worse than that. I think that what you just said isn't just an equivalent way of saying things. I think you actually just logically self-destructed, because you said that your theory makes exactly all the same predictions as Einstein's general relativity, but you also said that it's supposed to explain why I look older now than I did on my 10th birthday, and that's an observational fact. That's an experiment. Well, let me just finish the sentence. So if it's an experimental fact that I look older now than on my 10th birthday, and yet your theory makes exactly the same predictions for all experimental facts as Einstein's theory, then you have to concede to Einstein that his theory also explains why I look older now than on my 10th birthday.
The reason you think
I rest my case.
the reason you think I've contradicted is you're not listening to anything I say. I said I don't have a different theory. I have a different mathematics in which to write the same theory, right? It's not a different theory. I just don't think there's any illusion. Everybody up here saying there's some illusion. I think there is no illusion.
But you said,
Well, you don't think there's
you said
a
that you
special
can
present
explain
moving through.
why you
I
said
think
that,
that's wrong, right?
yeah, and you said you can explain why I look older now, and that
yeah.
Einstein cannot explain why I look older now, right?
No, I didn't say that.
Didn't you? You said
No.
this is the more.
I said it's a fact that I'm getting older. It's not an illusion I'm getting older all the time. And it's not an illusion
we're
I can
not
make a
saying- we're not
decision
saying
about what to
that
have
that's an
for dinner
illusion.
tonight.
Nobody
And can't make
denies
a
that.
decision about
Nobody
what to
denies
have
that
for
future
breakfast.
states of the world
What?
correlate with older states of your body, of course.
But that has nothing
and
to do
past
with
states of the
time.
world.
That has nothing to do
Well,
with
of course
time.
it does, 'cause
Tanner
the past
states,
is-
Tanner
you're
states
saying
of,
the past and
Tanner
future have
states of
nothing
my
to do with
body
time.
correlate with being in different parts of the world. That has nothing to do with time.
Well, we're talking about later states and earlier states.
That's
Has
right.
that
There's
got
a
nothing to do
fundamental
with time?
distinction between earlier and later. It's
Well,
not an
yes,
illusion.
but that
let me
has
ask
something
you a
to do
question,
with time.
Tim. If I've got two models, so I could generate one
picking on
space-time
yours.
model with
That's
the
okay.
earlier than relation, and I
Yes.
could generate one with the later than relation.
Sure.
Are they the same, or are they? Or is there some difference?
Look,
I mean, is
the
there
original
some-
glass we had falling. Let's think about what we thought about that. Here's something that happens all the time. Glasses fall and they shatter. Here's something that never happens. Pieces of glass recombine and jump up.
And we know
Now,
the
no.
What do those arrows have to do with it?
The only difference between those is the direction of time. The direction of time is not an illusion. It's not
I
something
don't see how
invented.
the way you
Einstein's
generate the
theory explains
space-time
it.
explains
It's the
that.
direction of
gravity also
states
explains
of the world.
Again, this is not a contrary theory to relativity. Maybe if I repeat something enough times, it'll get through.
Can you perform an experiment to show that time is an illusion?
Well, I would turn it around the other way.
Well, can you? I mean, we
Well,
prove things. If
right.
you have a theory that time is an illusion, what experiment, what data can we collect
No, I'm
to show
saying
that's
that
an
the very
illusion?
notion that time is flowing is an philosophically incoherent one that has no basis in physics, and somebody who claims that time is moving had better show me the meter that measures
But
the movement of
you're
time.
claiming that time is an illusion. Show me the meter that measures that.
Well, can we measure illusions with
Well,
meters?
but you just stated a fact that time is an illusion.
Right.
Then if I
no,
state
not
a fact,
time.
there is
The
the
flow,
moon,
the flow,
I can
the
measure
flow.
the moon.
Right. The
There
flow
is the
of time.
ground, I can measure the ground.
Right.
There is an
Right.
illusion.
Right.
Tell me how I'm going to measure
well,
the
can we
illusion.
measure? Let me put it this way: can we measure the illusion of the rotating ballet dancer thinking that the world is rotating? Can we measure that illusion? I suppose if you've got wire your brain up and so on, you could. So I suppose that you can wire your brain up and show the laying down of memories and so on. And you could even do experiments like what was Einstein said, that an hour in the dentist chair and an hour with a pretty girl, seem very different. You could probably measure that. But you need to talk to a neuroscientist, not a physicist. Because it's all about
Well, you're
neuroscience.
just shoving the problem off on someone else.
No. I'm saying that there's nothing about time. This is a property of psychology. And I guess these guys use meters. Yeah, I don't know. But I'm sure somehow you could measure what we're talking about.
You just
Probably
haven't
rather
figured
precisely.
out. You haven't figured out the experiment that would do that.
I've just told you the basis of it. Yeah. You put something
Yeah,
on your
but
head with wires into your neurones,
so the
and
only
you bring
way-
a pretty girl into the room, and then you have a conversation.
So the only way to measure time is our perception of time. That's what you're saying.
Because the flow of
can't
time
measure-
is our perception. Yes,
It's
that's
just
right.
the perception. We have a
Just
perception of
perception, 'cause
time
right.
because time is an illusion.
Right, because
So-
no, the flow of time. There's nothing in time itself that flows or moves. Okay, it's our impression of states of the world as they succeed each other. We have this illusion of movement, just like the rotation. We have an illusion of rotation. Okay, it's all in here.
Can you disprove that time is an illusion?
Disprove that time is an illusion.
Well, science says if you prove something, you have to be able to
right.
disprove
Okay,
it. Right?
so supposing we discovered that there was a second dimension of time, and we could say that this dimension of time is moving relative to that dimension of time, just like an object can move through space in time. Okay, that's what we mean by movement. If we had a second time dimension, then we could talk about it. In fact, I read a book when I was a teenager by a South African guy. What was his name? No. But long before that, about exactly this, that there are a whole sequence, there are infinite number of time dimensions, and each one is moving relative to the other one, because the notion of time moving relative to itself is meaningless. So what was the name of this guy? Dunn. John Dunn. Dunn, anyway.
Okay.
Can I just make a comment? Because
Please.
again, we're hitting the source of a lot of this confusion. Okay, so we've heard several times, there's a certain claim that's meaningless. Time passes 1 second per second. That's meaningless. What could that mean? No, wait. What else could it be? Here's something that's not meaningless. Think of the notion of a fair rate of exchange between currencies, yes? So there's a fair rate of exchange between dollars and euros. That's a good number, whatever it is. It's dollars and yen, that's a good number. Dollars and dollars. Man, there's a fair rate of exchange between dollars, and it's 1 for 1. I don't have to check. If you think it's something else, I'll trade with you.
I'm not saying a word.
Right. So there's this idea. Just a bad argument that because there's only one, as it were, rate that time passes, that's meaningless. It doesn't mean anything. It's perfectly meaningful to say you can only exchange money fairly, dollars for dollars, 1 for 1, even though you don't have to check.
Yeah,
I don't have to go into a laboratory and measure that.
In that same sense, space flows.
No,
1 meter
it
per
doesn't.
meter.
There's no directionality to space. There's a
1 meter,
directionality to time. There's
well,
no
that's what you
directionality.
do an arrowhead.
Let me try to inject a little bit of experimental viewpoint into this, because I think we've gotten dangerously close to now telling our universe a bit about how we want it to be to conform with our notions about what we feel comfortable about. And ultimately, I feel our job as scientists shouldn't be to tell our universe how to behave, but to look at her very carefully and see, how does it work? And what I think we've learned so far is, by looking very carefully, is that we have a pretty good idea of what happened during the last 13.8 billion years. We have a much shadier idea about a lot of ideas for what happened before that and what's going to happen in the distant future. But there's also a frontier of our ignorance beyond which we're really quite clueless. And we should be honest for Truth in Advertising and air our dirty laundry here and say that we are very confident at talking about time only in domains where we have a lot of clocks, either man-made clocks or nature-made clocks like atoms. Yet, very early on, and in the very, very distant future, there might be situations where there are no clocks. And I'm not just talking about digital watches now, but I'm talking about atoms. If all of this stuff has somehow been destroyed, if we just have some kind of soup where nothing is changing at all, where nothing is happening, then we can't do any of Einstein's games to define space-time through clocks and cleverness. Does it even make sense to talk about time flowing? And can there be time in any meaningful sense without change? If nothing is happening, does it make sense to talk about time flowing? I'm not claiming I know the answer. I just want to throw this question out here because it may very well be that rather than getting stuck into the question about whether there's a north or the North Pole, which is classical general relativity, when we embrace quantum mechanics and successfully managed to marry it with relativity, which we haven't managed to yet, we might actually end up with a situation where we have some kind of fuzzy situation where time as the time we thought we knew so well.
It could be an emergent property.
Yeah, it's an emergent property.
Yeah, so we're assuming time here is primitive.
Yeah.
It's a basic concept.
Yes.
So it's
physics,
still emergent.
Could be.
Yeah.
Could be.
Well, it's still in its birth.
I think
well,
now,
you see, it turns out, as Max says, when you apply quantum mechanics to the universe, it gets much more subtle. And it could well be that the world that we perceive, which has what we would in the trade call a quasi-classical spacetime that we see all around us, might be something which is very special state of the universe. So it emerged from the ferment of a quantum Big Bang, and it congealed into this sort of quasi-spacetime, quasi-classical spacetime, but it may not be fundamental.
Because you have all discussed
running out of time.
Einstein's theories of relativity, and this is related to space-time, and quantum mechanics, which you bring up, cannot yet be even united with this theory.
That's right.
We've got to come back
So
next
we have to
year
go all over again
and
have this discussion some other time when this has happened.
Well, which I think means that also studying the question of time and what it really is isn't something which is of interest merely because it's fascinating philosophically speaking, but it's also related to all of the most difficult unsolved problems in physics. And I think none of us can confidently say we know what the ultimate theory of everything in physics is going to be, but I think whatever it is, really understanding the nature of time is going to be one of the key ingredients of it.
Well, that's a good way to end. We've run out of time.